Hello everyone. In this video, we will study vector valued linear recursive equations. So let me start with recalling the linear recursion formulas when we were working with scalars. So a linear recursion formula is something like this. So x at t plus 1 is multiple of x at t. While here, and then x0 is given, initial value. And what we know that xt is just a scalar, so it's a number. It's a number which depends on t as t changes. It's a function of t. Then we learned that we can turn this recursion formula into an explicit formula by just knowing that, okay, x at 1, just using the equation there, it will be lambda times x at 0, which is lambda times x0. How about x2? x2 is by equation lambda times x1, but we already found that lambda times x1 is, x at 1 is lambda x0, so I plug in, I get lambda squared x0. How about x at 3? Well, it's lambda x at 2. X at 2 is lambda squared x0. So we have lambda times lambda squared at x0. And you multiply, you get lambda to the power 3x0. And if you repeat this pattern, you notice that in general, x at t is going to be lambda t to the power x0. Well, this is something that we worked at the beginning of this course a lot, and we did some works there. But now I want to change the scalar valued sequence by vector valued. And here I'm going to have vector valued linear recursions. So in other words, x at t is not just one number. It has components. x1 at t, x2 at t, and it can go up to xn at t. Okay? And while we have x at t plus 1, so this is the recursion formula. Okay, so let me just do this one. X at t plus 1 is equal to, well, a multiple of x at t. But that multiple doesn't need to be a scalar. It can be a matrix. So my general vector valued linear recursion would be of this form. X at t plus 1 is a matrix, which is n by n matrix, times x at t. And similar to the scalar case, we can have, we are going to be given the initial value. So x at t equal to 0 is going to be a vector x0. Okay, now the question is how do we find explicit formula for this one? So we want to find a formula for the vector x at t similar to the one that we found for xt for the scalar recursion. Well, the argument would go exactly same way. Instead of having lambda, now you have matrix A, and lambda to the power t will turn to a to the power t times x0. So the argument that we gave up there will work exactly here, but you have to be very careful. Computing powers of a square matrix is an expensive operation. In other words, it will take you forever to find a2. Well, let's see this in one example, and you will notice that how it will work. So if my matrix A, if my matrix A is given and it is okay, if A is given and it is 5, 6, negative 1, and 0, then, well, try to find A squared or A cube or A to the power in general t. What is the formula for A to the power t? Well, let me just calculate A2 and you will see that it will take forever for us to do the power. So 5, 6, negative 1, 0 times 5, 6, negative 1, 0. So the first component is 5 times 5 minus 6. It says 25 minus 6, which is 19. 5, 6 times 6, 0, that is 30. Negative 1, 0, 5, negative 1 is negative 5 minus 0, and the other one would be negative 6. That's A2. Well, what about A3? So you have to multiply that by another time, by A another time. A4, you have to multiply. But you see that calculation of matrix power always needs lots of work. Well, there are techniques. Actually, we are very close to those techniques, but we won't cover in this course. That using some advanced techniques, we can, one can find that A to the power t will be something like 3 to the power t plus 1 minus 2 to the power t plus 1, and 2 times 3 to the power t plus 1, that should be t plus 1, minus 3 times 2 to the power t plus 1. Then that would be negative 2 times 3 to the power t plus 3 to 2 to the power t. And that component is going to be negative 3 to the power t plus 2 to the power t. Yeah, so as I said, we are close to that technique, but we won't cover here. It needs a little bit more theory here to be able to do that formula. But we are going to, well, if someone gives you a t, then I can say that, okay, a t to the power x0 is going to be our explicit formula. Yes. Well, we did calculated a t, then we want to multiply a t to x0. But we know that a t takes a lot of work. What if we have a technique that we don't calculate a t then multiply it to x0? We do some calculation from the beginning which involves x0 itself. And this will be done because of this very nice fact which says if you have an eigenvector of matrix A, so if V is an eigenvector for eigenvalue lambda of matrix A, then A to the power n V is going to be lambda n to the power V. Or, okay, so this means what? This means that when you're multiplying A to eigenvector, you don't need to be worried about the powers of A. You just eigenvalue, if A times V is lambda V, then A to the power n is going to be lambda to the power n V. Well, instead of n, I will put t here just to be consistent with what we had up there. So multiplying powers of A to eigenvectors are easy to deal with if you know what are the corresponding eigenvalues. Well, Let's see how we can use that trick in an example. Find explicit formula for xt for which we have this recursion formula x at t plus 1 is 5, 6, a matrix times xt, but that matrix here specifically is given 5, 6, -1, 0, the example that we worked on in the previous example, times x at t. And the initial value is given here, it is 1 and 1 and 1. Okay, so here are the steps that you have to do. Note that xt has two components, x1t, x2t. So here are the steps that you have to take. First thing is you find eigenvalues and corresponding eigenvectors of matrix A. While specifically what we are interested in, or in our cases, these eigenvalues are going to be distinct. So for examples that we are working with, we are going to have distinct eigenvalues. Okay, so we find eigenvalues and corresponding eigenvector. Yeah, so let's see what does that mean in a case of our matrix. Well, you can do this one yourself. So DIY, do it yourself. There are two eigenvalues, lambda 1 is 2, lambda 2 is 3, and eigenvector for eigenvalue lambda 1 is an eigenvector, is -2 and 1, and for lambda 2 is -3 and 1. Okay, you can do this one. So we have done lots of examples here, so you can do it simply here. That's a step 1, find eigenvalues and corresponding eigenvectors. Step 2, write the initial value, the vector x0, as a linear combination of eigenvectors of the matrix A. So in other words, we are trying to write 1, 1, the initial value, as C1 times V1, the first eigenvector, plus C2, V2. Well, if you multiply C1 to V1 and C2 to V2 and add them, the first component is going to be -2C1 minus 3C2, and it must be equal to 1, the first component on the left hand side, and C1 times 1 plus C2 times 1, it must be equal to 1. So now we have a system of linear equations. We try to solve it, yes. So again, this one you can do it yourself. It's simple. We have done lots of examples of this form. C1 must be 4 and C2 must be -3. So in other words, we wrote the initial condition 1 and 1 as negative, actually 4 times, yes, 4 times vector eigenvector for lambda equal to 2 and -3 times eigenvector for the eigenvalue, the second eigenvalue. Okay, that's the second step. We wrote the initial vector as linear combinations of eigenvectors. Now use the fact that A times any of these eigenvectors, so A times V1 is lambda 1 V1, yes? If it is A to the power n, that will be lambda to the power n. And if you do this one for lambda V1, that will give you V1. If you do V2, it will give you V2. So we write that and we try to use that fact to calculate A to the power t times x0, which is just 1 and 1. How do we see that? Well, we will use that linear combinations that we used or we found in second step. So okay, so a to the power t, a to the power t at 1 1. 1 1 we wrote it as 4 times v1. Yep. So 4 times v1 minus 3 times v2. Now you can multiply, expand that inside, so you get a to the power t times 4 v1, which is the same thing as 4 a to the power t v1 minus 3 a to the power t v2. Okay, see, now v1 is eigenvector. A to the power t v1 is nothing but 2 to the power t v1. Okay, and a to the power t v2 is negative 3, actually, or was it 3? Just 3, yes, 3 to the power t v2. Okay, in other words, we found a to the power tx at multiplied at x0 is 2 to the power t plus 2. 4 is 2 to the power 2 times v1 minus 3 to the power t plus 1 v2. 3 times 3 to the power t is 3 to the power t plus 1. And if you plug in what was v1, so remember that v1 was negative 2 and 1, so you multiply, yes, negative 2 and 1, so you multiply 2 to the power t plus 2 to the negative 2, and 1 times t to the power t plus 2. That's the first part. And then negative 3 to the power t plus 1 times v2. v2 is negative 3 and 1. So you multiply that to that, 3 to the power t plus 1, and then 1 times 3 to the power t plus 1. Okay. Now, okay, I can add the components and write that x1t, x2t, this was xt, has the first component as minus 2, well, 2 times t, 2 to the power t plus 2 is 2 to the power t plus 3. And then there's that negative times negative, that will be 3 times 3 to the power t plus 2. The second component is 2 to the power t plus 2 minus 3 to the power t plus 2. So we were able to find a to the power t. So the first component x1 has explicit formula given by first component, x2 has explicit formula given by the second component. And this is how we solve vector valued linear recursion